get that one. So I have to take a place at least 30 from.
Click on it. Just click on time.
Yeah.
Just make sure it's focused on that screen.
That's how complicated we thought.
One, maybe the other one.
Yep. I know. I stopped by your office many times. I'm never in my office.
So nice to see you, Lisa.
Yes. Good to have everyone back. It's been lovely here this summer.
So we're also recording your face, and it's going to be, so it's pointing there, so if you can just...
Okay. I'll try
So
to
if you
stay
want-
still. I don't stay still much, but I'll try. If I get out of it, just...
It's actually goes from this corner till the end of the screen, so that's the range.
Okay, if I'm out of it, just...
I actually can use the camera.
Ready? Well, good morning, everyone. This is our SEO OR seminar, and today is my great honor and great pleasure to introduce our speaker from MIT. Well, you can see the big crowd of people like MIT. So
I thought we liked simulation-based stuff.
yes, both. They like both. Well, Professor Carolina Osorio, she's really outstanding. She's only an associate professor at MIT, but she has gotten all kinds of awards. That's why I invited her here. And very outstanding, including the Earnest Career Award, which is considered as the one of the yes. Yes.
Actually, you hadn't joined yet, but afterwards.
Oh, was that? No, I did yours.
You did another one.
I did.
Yeah. Good. Very
Then yes.
That's very good. So this is a very outstanding person, and she's a faculty member at both civil engineering at MIT and also the Operations Research Center. So she has been working on the operation research methodology plus the real application in the transportation in the civil engineering. Very, very interesting application. A lot of the high dimension, very complex real life application problem of the OR methodologies. So very, very, she's going to give us a talk about simulation, optimization, and with some applications. Welcome, and thank you very much for coming. And she's going to fly to Dubai tonight, so thank her for making all the schedules, squeeze the schedule, and come to give us a talk. Thank you.
Well, thanks everyone for making it. It's really fun to give a talk in such a crowded space. So I'm Carolina Osorio. I have an OR background. I guess most of you are from SEOR. But since my OR PhD, I pretty much went more and more towards transportation. I'm now in a civil engineering department. And so what I'll do today is I'll assume most of you don't know much about transportation. I won't go into too much traffic-y stuff. But I will start off by telling you a little bit about what I think is exciting for OR in the urban mobility and transportation space, and where I think we should be going, where I think we need to work more. And then I'll focus in simulation-based optimization, and we'll go through both continuous problems, discrete problems, show you some improvements or enhancements we've made to some existing techniques, and then a very long list of things we need to do and we haven't yet done.
Maybe other button?
Or you need to point to the
like
Where
this.
do I
Try
point?
that. Try now.
Yeah.
Just press on.
Okay,
there we go.
some big word. Okay.
Oh.
Okay, so what's nice about working in transportation is that even though most people don't work in it, they all are familiar with it, right? They all suffer in their morning commutes, and so it's a very intuitive problem to talk about. There's a few things in the last, I would say, 5 to 10 years that are really changing the transportation world. And when I say transportation, I think typically urban transportation. And that's the fact that a lot of private stakeholders are now major players in providing urban mobility services, which in the past, was mainly governmental agencies that were in charge of coming up with services. And so that meant also that the pace at which we would have, really interesting innovations in the mobility space was much slower. They were much more, I would say, risk averse. now we have, huge companies, all the major tech companies have some stake right now in providing new services, and so that means that there's a variety of really new on-demand mobility services that are being offered. For OR, that presents a variety of really big challenges. On the positive side, that means we now have access to really neat high-resolution data that we can work with, and that can help us, relax a little bit the modeling assumptions we're making in our approaches. But that also means that, on the one hand, the types of things we want to model are much more complicated than 5-10 years ago. So a lot of these tech companies, they're really interested in on-demand mobility, so real-time services. How do I price in real time? How do I tailor my prices to individual characteristics? How do I make more personalized, user-centric services? And so these are things, when we think of our traditional math programming approaches maybe to design services, we weren't as interested, mainly because we didn't have the data and we couldn't really describe supply or user behavior in that level of detail. Now we do. And so that means that we're going more and more towards more high resolution description of demand, of supply, and how they interact, and very heavily relying on the data. The other aspect of it is that now, especially with our smartphones, everyone that travels or commutes is like a real-time optimizer of their trip, through their apps. And even though they might never have heard the word optimization, they're looking at Waze or Google Maps in real time and deciding what mode to take and whether they should reroute, etc. So that means that the actual traffic patterns are really changing in real time. And now if there's an incident 2 hours far away from where I am, in real time I'm going to get information that might change how I route, even though I might not be going close to where that incident happened. And so that also means that the models that we're developing and need to use actually have to cover very large urban areas. We can no longer, even if I'm making a local change to maybe a couple intersections, I can no longer afford to just use a model that models those couple intersections. I actually have to look at a city scale, a full, maybe even metropolitan scale. And so we definitely need optimization techniques that can handle very large scale problems, both in terms of the spatial scale, but also in terms of the dimension of the decision space. And so usually when you think of very high resolution data that we're using, high resolution models, and on the other hand, very scalable techniques, there's a trade-off there, right? Usually very large scale problems are solved with much simpler models, and when you use very high resolution models or data, you actually have a trade-off and solve much smaller scale problems. So that's the space we've been working in. How do you get the best of both worlds, basically? So this is a plot where you say, what is the modeling detail or level of resolution? In transportation, we have different families of models. And then as you increase the level of detail, typically you have less tractable models, right? And so they're less efficient or made for optimization. So something that we call macroscopic models, you can just think of traditional math programs, maybe analytical queuing models. So really nice, often differentiable analytical formulations that aren't very detailed in how they describe demand and supply, but are really nice for optimization. And then as we go towards more increased levels of detail, we have, for example, simulation-based models. The transportation community has worked extensively on specifying very nice simulation models that describe in detail, especially demand. How does demand vary across the population, across space? And so that they become simulation-based, and they become less easy, let's say, or tractable to actually be used for optimization in general, and let alone for high-dimensional optimization. So everything I do is basically thinking about, can we one day end up in this point where we actually use models that have high level of detail, that rely on high-resolution data, but at the same time can solve very high-dimensional, large-scale problems. So that's my end goal by the end of my career. I hope to get somewhat closer to that point. In transportation words, or more general words, the way I like to think about what I'm aiming at with my work is, how can we develop tools to enable the use of microscopic data and models? So microscopic means it's data that's collected at the scale of individual travelers or individual vehicles, so through your smartphones or maybe sensors on your cars. How can we enable the use of this data and models specified at that scale to optimize networks at a much larger urban scale, like full cities or metropolitan regions? Okay. That was on purpose, so I would actually pause and breathe and give you time. Okay, so I do have an OR background, and when I did my PhD, a network was a network, and so I did a little bit of biology networks, I did healthcare networks, I did transportation networks, and then towards the end of my PhD, when I was actually doing the transportation, I really got excited about it. And since then, everything has been about transportation. And the general, let's say, philosophy of how I work is how do you take general purpose OR tools, particular optimization algorithms, but also models, and tailor them, providing more transportation problem structure so that they actually become relevant and useful for practitioners to solve pretty tricky problems. So everything I do is very much related to what do practitioners care about, working with public and private stakeholders. So the problems they come with are, really tricky. Elise probably knows much better than me. They typically don't fall into the nice categories of assumptions that we make with our, traditional math programs. Convexity, for example, is something that often is not satisfied. The simulators that they use are pretty tricky, sophisticated simulators, and so they're very computationally costly to run. So they're very challenging problems, but at the same time, if you can come up with techniques that can give them a better solution, not by any means optimal solution, but a solution that significantly outperforms what they're doing in the field, you can potentially have a good impact in practice. And so that's what we're aiming at, developing with the different stakeholders techniques that can give them better solutions, not necessarily optimal ones. Part of my work, which I won't talk about today, is this arrow. So taking traditional, what are called macroscopic models in transportation, making them a little bit more detailed, basically going from deterministic formulations to probabilistic formulations to account for uncertainties of demand and supply, but still allowing them to be tractable. That is not of interest to this community because it's basically much more traffic flow theory oriented. There's queuing theory as well, but a lot of trafficy stuff. So what I'll talk about today is mainly based on this second arrow. How do you take detailed either mobility data directly or detailed simulators of traffic and transportation and enable their use to optimize problems? Now, I use the word optimization loosely because the techniques that we developed, what we do typically is take general purpose optimization algorithms that have nice optimality convergence guarantees, and then think about how do we improve their short-term performance? How can they come up with really good solutions within hours or days or a time frame that is orders of magnitude smaller than what is traditionally used. Okay, so you don't end up necessarily with full optimal solutions, but significantly improved solutions compared to what you started off with. And the general idea of everything I'll talk about today is exploiting problem structure. So how do you specify traditional transportation models or such analytical models such that they have some problem-specific structure that you then give your general-purpose algorithms, and through that problem structure accelerate the ability of these algorithms to identify good solutions. So that might be very abstract, but I'll give you some examples of what that means in a second. This is a dense slide, so I'll just tell you the main things about it. The key family of problems we're going to be looking at are simulation-based optimization problems. So X is my decision vector. I cannot really observe F accurately. I can estimate it by running or evaluating a simulator, so I can get estimates of f of x. And I assume that my constraints are not simulation-based, they're analytical and differentiable. Other than that, I don't make assumptions on the constraints, but we don't have simulation-based constraints. And so typically in the literature of simulation-based optimization, a lot of it accounts for the fact that you don't have a closed form expression for f, right? That you can only evaluate and you only get noisy evaluations. And the fact that you don't know much about the properties of f. Okay, so the algorithms are really nice because they're designed for a very broad class of families, and they can have convergence guarantees even without imposing very strong assumptions on it. The specific challenges in transportation when you try to do simulation-based optimization for transportation problems are, number one, that the simulators we use are much more computationally intensive than what we would use, let's say, to evaluate a general purpose algorithm. So these simulators can take hours, maybe even days, to evaluate one point, depending on what performance metric you're trying to evaluate. So definitely the idea of coming up with a good solution within few simulation evaluations is important, because few is still a matter of days, maybe hours if it's much faster, but definitely not in the matter of a couple of minutes. So the notion of having a computational budget, a fixed amount of runs, or a fixed computational runtime within which you have to come up with a good solution is very relevant in the transportation space. And the other aspect that makes this problem difficult in transportation is we often are looking at very high dimensional problems compared to, I would say, what the traditional simulation literature is looking at. In the continuous space, I'll show you some examples today that look at problems with tens of thousands of variables. In the discrete space, we're still looking at problems with probably about 100 variables, or 200, 300, not yet at the point of thousands or tens of thousands, but eventually we want to get there. And the traditional transportation problems, also in the discrete space that we've addressed with analytical methods, they're definitely very high dimensional problems. And so we definitely need techniques that, if we were to want to address them with simulators or with more detailed data, we need techniques that can scale to that level. So scalability or problem dimensionality is one major aspect, and computational efficiency is the other aspect. Okay? So we need to come up with good solutions without having to run too many times the simulator, sorry. So the general idea I work with is called metamodeling. I didn't come up with this, so this is a very traditional approach in simulation-based optimization. So this is the problem we want to solve. F of x is this unknown simulation-based objective function, and metamodeling basically says, at every iteration k of my algorithm, I'm going to solve an analytical problem. I'm going to replace my objective function f by an analytical function that approximates f. And so this is the function mk. It depends on my decision vector x and some coefficients beta, which I'm going to estimate such that m of k minimizes some distance to f over the set of sampling points. Okay, so in this problem, it's purely analytical, and the information from the simulator comes through the parameters that I can estimate. Okay, and so the key thing here is that there's an index k, which means that at every iteration of my simulation-based optimization algorithm, I'm going to update my analytical approximation, this meta model, and then I'm going to solve this approximate problem. Okay, and I do that. So every time I solve this problem, I can come up with a trial point, a new solution. I can then simulate that point. I can simulate other points that I might want to. For example, I might want to do more exploration. And then based on that, I can re-estimate the coefficients and resolve this problem. So solve a purely analytical differentiable problem and get a new solution, right? And I can do that iteratively. Okay, so eventually, as your sample size grows, as the number of points that you sampled increases, you would hope, number one, that MK, your meta model, becomes a better approximation of F, either locally or globally. And you would hope, hence, that solutions to this problem are actually good solutions to that problem. Does that make sense? Any questions on that end? Okay. So in the literature, in the general literature, there's been a lot of work on meta modeling, and the main approach has been to say, let's take a general purpose meta model. It can be a polynomial, it can be a quickening function, something that, I know what the nice mathematical properties are, and that it's still very relevant for a very broad family of problems. The challenge is, you're using and treating your simulator like a pure black box. You're not coming up with a functional form that is specifically for one class of families F a good approximation. And so typically what happens is you need to actually simulate a lot before that general purpose function actually becomes a good approximation of your unknown function F. So what we've been working on is, in transportation problems, there's a lot of problem structure that you can exploit. Can you formulate a problem-specific approximation of F that we call here A of X? So an analytical approximation of F, which is problem-specific, so you already know what F is, and you come up with your function A of X. And then, since that's a simplified approximation, it, for example, might not be time-dependent, it's definitely not going to have the level of detail that your simulator has in terms of describing demand and supply. So the idea is correct for that simple approximation by parametrically, and in this case by some scalar term here, beta k0, and an additive error term here that is your favorite choice for a general purpose meta model. So we often use polynomials here, so phi would be a polynomial function x with coefficients beta. Okay? So the idea is exploit some problem-specific information. Don't treat your simulator purely like a black box. Formulate A, and hopefully if A of X is a good approximation to F, then very quickly you can come up with good solutions. So good solutions to this problem that end up being good solutions to this problem. Okay? Intuitive, right? Any questions on that?
So what is capital Phi again?
So the idea is, if you define your meta model M just by your initial guess, A of X, it's what we call a low fidelity approximation. And so you think of, I would like to correct for it parametrically based on simulation observations to make it a better approximation. And the idea is to do it first through some scaling term, if the magnitude of A of X is off, and also some additive error term. And so phi can be any general purpose functional form.
Some statistical model.
Yeah. So we use just polynomials in X and fit the coefficients beta, but it could be something more problem specific if you wanted. The key about phi is that you should be able to satisfy nice asymptotic guarantees with it in terms of how accurate M of k, the distance, you can bound uniformly the distance between M of k and F. So phi, should be a general purpose function. to be able to guarantee that.
And what's the dimensionality of x in your case?
So it depends. I'll show you some problems in continuous space where x is up to tens of thousands of variables. In discrete space, we've only gotten to, I think, 400, 500 variables. Yeah. Okay. So graphically, here is intuitively how this works. So the left, this is a two-dimensional problem. It's something called demand calibration or origin destination matrix calibration. I'll talk about it in more detail in a second. For now, it's just a two-dimensional problem. This is dimension 1, and this is dimension 2. And this is if I actually do a somewhat detailed grid search or grid evaluation, almost exhaustive evaluation of f, this would be the estimate of f that I end up with. So this is my simulation-based function pretty much evaluated everywhere in the feasible region. It's a pretty ugly function to optimize, as you can see. And this is the point where, according to my current estimates, there could be a global minimum. So this is a problem I really want to solve. And this would be an example of an A of x function that we've used, which is basically just a system of linear equations. So this would be the same first decision variable, second decision variable, and this would be the A of x, this whole thing. And so if you compare your left plot with the right plot, it's not a good approximation. If you ask me if this is a good approximation of that, I would say no, by no means. It turns out that on the one hand, you have a global only one global minima. You definitely don't have any local minimas in here, which you do have here, many of them. But the global minima in terms of where it is not too far off in terms of where the true global minima is. So the question is, if I give the algorithm this information, can I help it find very quickly subregions of the feasible region that have promising points? Okay, and here I've compared the performance of two algorithms that are identical. The only aspect in which they differ is actually one of them uses A of x and the other one doesn't. So the other one you can think of setting beta 0 to 0, and so only has a general purpose function. So if we start off here at the initial point, remember the global minima is here, so it's around here. The red line is the general purpose algorithm where you don't give it the A of x information, the problem specific information. So you don't give it this information. Basically you'll see that it goes through a variety of iterations. Eventually it does end up in this neighborhood, but it takes a certain number of iterations, whereas the green line is if you take the same algorithm and now actually give it this A of x information, well, from the very first iterations, it's going to end up in that neighborhood. So, okay, in this two-dimensional example, it seems nice. The question is this actually helpful for actual, more complicated transportation problems, and also how does this scale? Okay? And so one aspect of why this is difficult, before I show you some examples, is A of x. So remember, this problem, this meta model problem, is a problem I solve at every iteration of my simulation-based optimization algorithm. So I need to be able to solve this problem really fast compared to simulating, because if it takes too much time to solve that problem, I'm probably better off evaluating my true function and estimating f of x than solving an approximate problem. Okay? So solving this problem has to be done in relatively fast compared to simulation, which means that A of x has to be able to be computed pretty much instantaneously for high-dimensional problems and large-scale networks. And so if you want A of x that is computationally very tractable, often that comes with a cost of maybe a function that is not such a good approximation, A of x, of the true function f of x. So the real challenge for transportation is formulating functions A of x that have a good trade-off between being able to evaluate them really fast, so I can solve that problem fast, but at the same time that are still a really good approximation of the underlying function. So that's the main challenge we've been working on for different classes of problems. And let me show you some examples and some specific instances of what these meta models will look like. So this is something called origin destination demand calibration. It basically says, I have an urban area, a city, a metropolitan area, and I want to estimate travel demand. I want to estimate, for example, from 7 a.m. to 9 a.m. Every 30 minutes, where are people traveling, from which origins and which destinations. So typically the urban area is segmented into zones. Okay, so we don't try to estimate individual trips. We say for a given zone or a pair of zones, an origin zone and destination zone, how many people on average want to go from the origin zone to the destination zone at 7 a.m.? How many people want to go at 7:30? How many people want to go at 8? Okay? So basically that's what we call demand calibration, estimating how demand varies over space and over time. And the calibration problem is often formulated in this way. So you have some sparse measurements of, for example, traffic measurements that you observe in your city. So speeds on certain roadways that you've measured, flows, counts of vehicles on certain roadways. And this is what we call these YIT. So YIT could be, for example, the speed observed on link I at time t. Okay? So what you want to estimate, let's say I want to estimate demand from 7 to 9 in increments of 30 minutes. So I want a demand estimate from 7 to 7:30, 7:30 to 8, etc. And then for each one of those 30-minute intervals, I also have these field measurements on some links. One of the challenges in this problem is that the set of links for which I have measurements is very sparse, something in the order maybe of like 10% of the links in the network. So by no means do I have a lot of data. And the goal of this part of the objective function is, can I come up with demand estimates such that I minimize the distance between my field measurements? So, for example, speeds I observed on a certain highway from 7 to 7:30, 7:30 to 8, compared to the estimates I obtained from my simulator. So this would be, if this is field measurement speed on link I at time t, this would be the expected speed according to my simulator on link I at time t. Okay? And the goal of this part of the objective function is to say, I want a demand estimate that gives me simulated traffic conditions similar to what I observe in the field. The second term I won't go into detail, but basically the problem is underdetermined. And so this is a term that we add to the objective function to try to regularize it. Okay, I won't go into detail. Does that problem make sense? Clear? Okay. So this is typically a very high-dimensional problem because the way we discretize space, you end up with hundreds, thousands of different zones in an area, and on top of that, you want to estimate demand over time. Okay. So very often you'll have thousands, tens of thousands of variables that in your objective function. And the typical approach in transportation is to take general purpose continuous simulation-based optimization algorithms, SPSA, simultaneous perturbation, stochastic approximation is one that the community has loved, and there's extensions of it to try to make it better for transportation problems. But in general, the challenge we've had in transportation is that these general purpose algorithms are not designed to be terminated with very small samples, let alone for such high dimensional problems. Yet that's how we use them, both in research and in practice in transportation. And so one of the things we've been looking at is, can we take some of these general purpose algorithms and by embedding these meta models, come up with much better solutions fast. So I'll show you some examples we've done some work with a Singapore case study, and this is a Berlin metropolitan area case study of how the algorithms work. So first I'll show you how it works, then I'll tell you a little bit about the meta model. This is the traditional performance that we get. So the x-axis is the number of iterations. It goes here from 2 to, I believe, 50. This is 20, sorry. This is an example with Singapore. And here, so the red line is the algorithm that uses a meta model. Okay. The y-axis is estimates of the objective function. So you want small values, you're trying to minimize your function. And then here there's a set of both blue lines and black lines that are either SPSA, so a traditional algorithm used for this problem in transportation, or a generalized pattern search. So again, algorithms are not designed to be terminated with very small computational budgets. And so what happens is, if you start with some initial solution here, when you terminate these algorithms under small budgets, well, they can find solutions that improve compared to the initial conditions, but not, significant, definitely not improvements in terms of orders of magnitude. And that's traditional. They're designed based on asymptotic properties. They're seeing the simulator as a black box, so it's not really a fair use of these algorithms to terminate them with such small samples. Now, if you take one of these algorithms and actually embed the meta model information, you end up very quickly with orders of magnitude improvement in the objective function. Okay. One of the challenges that we're working on now is a lot of our performance results for different types of transportation problems, they look like this. So it's nice because it has a huge drop, typically 1 to 2 orders of magnitude improvement in the objective function. But it's not great because later on it just levels off. So one thing we're thinking about is, how can you use some of these information from the analytical traffic models to improve the performance across iterations, not just initially. And so there's a variety of ways to do that. This shows performance not in terms of number of iterations, but total computation times, and this is computation times in days. And the reason why this is important is because compared to SPSA, or for example, the generalized pattern search, we actually, by using the metamodeling approach, add some computational burden, because we're now solving at every iteration an optimization problem versus simply updating techniques of matrices, for example, in SPSA or in pattern search. Yet, even with that computational burden, you still see that there's significant improvement in performance as a function of runtime. I won't talk about this for now. So what do these meta models look like? And that's really where a lot of the work has been and the challenges have been for us. This basically says, so if we go back to our initial problem, what I want to approximate here are, for example, expected speeds on link I at time t, and my decision variable is demand, so spatial distribution of demand. This shows for one specific time interval, basically just a system of equations that says there's a certain level of demand, and there's a certain way in which people choose routes. So here with Singapore, it was a function of what are the travel times on the routes and what are the tolls on the routes, because there's actually some tolls, which are the red dots here. If I have a model that describes how people trade off different routes, how likely, what the probabilities of different route choices are as a function of travel times and cost, that's here, then that's going to lead to certain levels of demand across routes, which would then lead to certain speeds across the different links or roads of my network, which is part of my objective function. So basically, it's a system of nonlinear equations. What's neat about it is that we formulate it in a way that the number of nonlinear equations scales linearly with the number of links or roads in your network, independently of what the dimension of your route choice set, which in transportation is important because once you look at urban metropolitan scale networks, the dimension of plausible routes that individuals are considering is easily in the millions, tens of millions. And so here, at least, we have a formulation that you can use very large route choice sets, yet that's not going to impact the dimension of the system of equations that you're solving. So basically, if we go back to the general idea of metamodeling, here, to solve this problem, basically to get A of x, what I need to do is solve a system of nonlinear equations that scales linearly with my network size, the number of links in the network. So that I can do in a computationally efficient way, which means that I can come up with A of x evaluations relatively fast. So we did that for static problems, which means that you don't look at how traffic varies over time, and you just want to estimate demand over one time interval. And then we extended that to dynamic problems, dynamic calibration problems, where you actually want to estimate demand over not just space, but time. And there, we found something really interesting, and this is just the last couple of months, which is your initial guess would be to say, well, that means my A of x has to be time dependent, right? I need an A of x function that explicitly says, as a function of time, how does congestion propagate? And that is tricky, because if you actually want a time-dependent function A of x, it's very difficult to come up with a formulation that is also computationally efficient. And so what we did is something super simple, but it turns out it actually works, is for every time interval, so think of estimating demand from 7 to 9, where I group time for a 30-minute time interval. So I would have 4 different time intervals. So for every time interval, I use a time-independent formulation, the same formulation I use for my static case, but I know that, for example, speeds across time for a given roadway, they are correlated temporally. So we capture that correlation simply through the coefficients of the metamodel. The coefficients of the metamodel are estimated based on simulation observations, which are themselves correlated. So the speed measurements I get from the simulator for 7 to 7:30 are correlated with the ones I get from 7:30 to 8. So we use the correlation from the simulator to estimate parameters for each one of these time intervals. And so for each time interval, I solve a completely different optimization problem, as if it were static. So basically, I'm not capturing any temporal dependency explicitly in my metamodel formulation. For example, the analytical traffic model doesn't have to be time dependent. I'm only capturing it at a very high level through the parameters of the metamodel that are estimated through correlated data. Yet, if you do that, so it's a really simple approach, definitely tractable because you've now decoupled your problem. If you have t different time intervals, you've decoupled to solving t different optimization problems. So it becomes, again, scalable for high-dimensional problems. And then the typical performance guarantees that we see, and this is a Singapore example, are very similar to the static case. So very quickly you end up with an improvement, then it levels off. You really don't see much improvement later on. But if you are terminating your algorithm very quickly, you definitely outperform general purpose algorithms, which again are just not designed for that. So one thing that's really exciting about this, it means that when you think of metamodeling, you think, well, as my problem complexity becomes more complicated, so going from, for example, from static to dynamic, that means my meta model necessarily has to become more complicated, and very quickly I'm going to end up with a formulation that is not going to be efficient enough, and I'm just better off simulating versus solving an approximate, really complicated, time-consuming problem. But here, this is an example that shows that you can still use really simple analytical formulations for your meta model and capture a lot of the complexity through just the parameters that you're fitting. Okay? And that has led us to look at actually at real-time calibration problems, which are a level of magnitude in terms of actual computational budget, a level of magnitude more difficult. But I think some of these ideas are promising there. I won't go into the detail of this, it's a little trap. Okay, so the other aspect of continuous problems that we've looked a lot is traffic management, working with New York City Department of Transportation and with some case studies in Switzerland where I did my PhD. And there the challenges were, again, specifying the meta models for different types of objective functions. So for example, we did a case study looking at how does energy consumption or emissions vary if I change my traffic lights. And the challenges there were how do you come up with a nice analytical approximation of how traffic lights and hence supply on the roads impacts emissions or energy consumption. So where do we stand in terms of continuous simulation-based optimization for transportation? With these meta model ideas, we've looked at very different applications. So I mentioned signal control and demand calibration. We've looked also at congestion pricing. So pretty tricky objective functions in general. But the nice thing is we've managed through these meta model ideas to really address much higher dimensional problems than what the traditional general purpose algorithms are initially designed for. So the most recent example I showed you with the dynamic demand calibration for Singapore was with about 16,000 decision variables, looking at having really promising results for very large-scale networks. We've done case studies also with the Berlin metropolitan area, where you have tens of thousands of roads. And so now we're really, one thing I'm very excited about, as I mentioned, was the real-time aspect of it. And in general, the general conclusion of all of these studies is typically with the Metamodeling approach, you can use very small computational budgets, so running the simulator up to 100, 150 times. That's really nothing compared to the dimension of the problem that you're looking at, but still get improvements in the objective functions that are 1 or 2 orders of magnitude compared to the initial ones. So there's definitely lots of potential there to improve that. Yeah.
So when you say the 15 to 100 simulation one, does that include any replication or you only do one replication?
So typically when we think of the budget, we assume that we can parallelize the replications. And so we don't account for that. If you could not parallelize that, or for example, if for some reason you're actually considering different points for which the replication runtime might be very different, and so you would actually need to account for some notion of sequential evaluations, then in that case you would have to include it in the budget. But here, this is basically saying I can evaluate up to 100 points. Yeah. These are very, very tight.
Yeah, but still very small.
It's exactly super, super small. I think also the other thing to think about is as you increase this, which I mentioned before, is you have to think differently about what the added value of the meta model is, right? Because basically it levels off. So if I look at this, if I were to increase this to maybe 100 or maybe 500 by 1 order of magnitude, it doesn't seem like this is really the way to go. You would have to think differently about what's the added value of that analytical information if you actually have a larger budget. I think that this approach, as is not the way to go, because very quickly you learn a lot from your analytical model, but it's not designed to learn much more from it. So how did this carry over to discrete problems? So everything I had done until I would say 2 years ago was in the continuous space. But in transportation, I would say the vast majority of the really important problems tend to be formulated as discrete problems. And so I think there's a big importance to actually think of, can we come up with good discrete simulation-based optimization algorithms for certain classes of transportation problems. And this was also motivated by some work that we did with Zipcar and with Ford in car sharing, where they were interested in 2 aspects: estimating demand for their car sharing services for their mature markets. So initially we did Boston and New York, and we then extended that to San Francisco, Chicago, and Toronto. So estimating demand, and the other aspect of if you have demand, how do you operate your car sharing service? And in particular, the problem of where do you locate your cars? So this was in the context of what's called round-trip car sharing. So you have to reserve your car at a given location and return it at the same location. And you typically make the reservation in advance, not usually in real time. So maybe days, weeks in ahead. You could reserve it up to 30 minutes before you leave, but most of the reservations are done well in advance. And so they were thinking of tools for a problem that they solve every month, which is how do I rebalance these cars? So much simpler than the one-way car sharing system, which you would have to rebalance in real time. Here it's something that a problem you solve offline. And they had really neat data. So the first data set we had access to was all the reservation data for these cities. So basically all the bookings that had been made for this car sharing service. And a booking had the following information: the type of vehicle they used, the time at which the reservation was made, which is called a creation time, for what period the car was reserved, so the start time of the actual reservation, the end time, and what was the revenue of that reservation. Okay, and we had that for all the individual bookings that was made, so very disaggregate data. So then we said, okay, we want to use that data to optimize the spatial allocation of their fleet. How could we do this? And the main thing that I was most excited with that project is there's a lot of information in that data about, for example, how demand is spatially and temporally correlated, how it might be a function of what offerings I'm making, either because of the pricing or the vehicles that I'm making. And the traditional approach in transportation, if you want to estimate demand, is to step back and say, okay, I'm going to specify a model and say, what does demand depend on? So it might depend on price, it might depend on the vehicles, it might depend on my trip purpose. And then based on that specification, use the data to fit the parameters of that model. The challenge here, there's two things. Number one is the car sharing service is a service, like many new mobility services, that their competition is changing drastically every 6 months or year. So the reasons and the trip purposes and the motivations to reserve a car, I would say 2 years ago, is very different from how people are using car sharing services now. It might be very different from how they're going to be using it in 2 years. So the idea of stepping back and saying I'm going to specify a model that actually explains what is driving demand was something that we were slightly less attracted by, because we think that in many cases these models might not become as relevant given how new mobility services are really very frequently disrupting the mobility space. And the other aspect is if I do that, I lose a lot of disaggregate information in the data. I basically use this disaggregate data to estimate an aggregate model. And then it's nice for optimization because I now have a nice functional analytical form, but I'm using a lot of the rich information that is in that data. So what we did was actually think of simulating in the sense that we sample directly from that reservation data to estimate demand. So reservation is what would be called a truncated or censored version of demand, right? So if I wanted to reserve a car at location X time T, and maybe that car wasn't available, well, I could either not reserve, or I could reserve at another point in time space, right? And so basically what we observe is that end decision of what reservations were actually made, which is different from the actual underlying demand, right? So there's a truncation or a censoring process there. So we said, okay, we want to estimate disaggregate demand by sampling from the data. And so that would lead to a disaggregate demand, because you actually have disaggregate reservations, but you have to correct for that censoring. And so the way we did that was specify really simple models of with what probability does a given reservation get censored, and based on those probabilities have weights with which we sample. That might be a lot, but basically it's saying we take the reservation data, we sample from it, and we end up with a disaggregate set of potential demands for car sharing. That's what we call demand. And then what we really want to solve is this problem of how do you assign your vehicle? So X now is how many vehicles I locate at a given station. So it's a vector of Xi's, where I is a given station. A station is a location with several parking spaces. It could be 3 parking spaces, it could be 30. So how many vehicles I actually want to park for a given month at station A. And I want to, in this case, we wanted to maximize expected profit, which is the difference between expected revenue, a very simplified cost structure, and then I had some constraints on a maximum fleet size and a maximum number of parking spaces at location I. So if this objective function were analytical, this would be a trivial problem to solve. Okay, analytical and linear, it would be a trivial problem to solve. The challenge is we actually want to have a more disaggregated description of demand and supply and how they interact. And so we use a simulator, which is basically sampling from that data to estimate demand. And then with very few parameters describing for a given set of potential demands, which ones actually become reservations. Okay, so there's like 3 or 4 parameters in the actual simulator, but it is a simulation-based function. In this case, unlike the traffic problems I showed before, the simulator runs instantaneously. So here we could afford to actually do much more sampling if we wanted to. That's not really the main concern. So how does the metamodeling idea work here? So think of your favorite math programming that approximates this problem. So think of your favorite analytical approximation of how, for a given spatial allocation of v equals x, that would lead to some revenue here and corresponding x function. So pick your favorite math programming formulation. It would probably have a few more constraints to actually describe the interaction of demand and of supply, but g of a here would be the objective function from your favorite math program, okay? And then the meta model basically says, well, this is an analytical approximation of what's happening. It's very simplified in how it describes interactions of demand and supply, so I'm going to correct for it parametrically, just as before, a scaling term that scales my objective function of my math program, and then some here general linear function of my decision function. Okay. So the question is this useful, and is there any added value to actually using the simulator and doing this more complicated simulation-based approach versus just using the solution from my math program? Okay. So what does this look like? So the algorithm that we used was actually G's algorithm. So he developed this back in 2013. Called AHA, Adaptive Hyperbox Algorithm, and it was one of the algorithms that actually, in their test problems in the paper, had pushed it to high-dimensional problems. So there, in that specific paper, they actually looked at problems with dimension 100 and showed that it could perform really well. So that we thought was a great starting point for what we wanted to do. And what we did was extend AHA. So basically, AHA at every iteration has a set of points to sample, to simulate. And what we do is we add to that solutions from this mixed integer program. Okay, so at every iteration we just added a new type of point that we want to simulate, which are solutions to this mixed integer program. By extending it, basically we can preserve all the nice properties that AHA already had, all the nice asymptotic convergence properties are satisfied, and hopefully what we want is, by also simulating points that are solution to the mixed integer program, come up with good solutions fast. So let's see if that's the case. This is an example from downtown Boston. For those familiar with Boston, this is the South End. So the red dots are all the stations, the locations where Zipcar could reserve vehicles. And here we have a fleet size. We want to allocate about 100 vehicles across 23 stations. Okay. So how do the algorithms perform? So these are 4 different figures which have just different demand distributions. I'm going to focus. The trends are the same across figures, so I'll just focus on one figure. This is the iteration of the algorithm versus the estimate of the most promising solution, the trial point. Okay? And so here's a maximization problem, so you actually want high objective function values. So the dashed lines are AHA. Okay? So if you don't give it any information from your math program, AHA eventually finds solutions with improved performance. Sometimes it finds what it considers to be a local optimum fast, and so it will stop there. And the solid lines are if you, at every iteration, also give it solutions from your mixed integer program. Okay? And so basically the general trend is that there is, especially at very early on in the first iteration, an added value to giving it analytical information, right? Now then we said, okay, this is great, but then maybe something is happening just like in our continuous space where, what if you just initialized AHA with the solution from your mixed integer program? Is that good enough, or is there still an added value to actually resolving these meta-model mixed integer programs at every iteration? So this is what happens when you initialize AHA with the mixed integer program solution. That's now the dashed line. And then the solid line is you initialize it with the mixed integer solution, but then also at every iteration, you also allow it to sample from solutions from that parametric mixed integer program. And so overall, the trends are, there are cases like this where you really don't see much improvement. It seems like as long as you initialize AHA with a good solution, it's good to go. There are other cases where it seems like, yeah, there could be some added value in iteratively solving the mixed integer program, but it's not huge. Something we've done recently is actually comparing it to stochastic programming. And so there we see that depending on how good of an approximation your mixed integer program is, there's an added value to simulating or not. And so typically, for example, if there's a lot of congestion, meaning there's a lot of demand compared to the actual supply, then in that case there's a really good added value to simulating, because there you have a more detailed description of supply-demand interaction. But if you're looking at cases where most people find their desired reservation and they don't actually have to consider alternative options, there's not much truncation or censoring of the data, then your stochastic program will probably do just as well. We applied this to the metropolitan area of Boston. So again, here are the different stations of Zipcar. Here we want to allocate about 900 vehicles. There's across 300 plus stations. And this is how the solutions of the algorithm would compare to what Zipcar is currently doing. So the x-axis is a Zipcar metric, either profit or utilization of the vehicles. And the y-axis is the metric under the solution proposed by the algorithm. And this is evaluated through simulation, so it's not deployed in the field. But overall, it seems that there's some potential to improve both profit and utilization if you actually use the proposed algorithm versus what they're currently doing in the field. So this led us to work with them. Now we're doing two things with them. One is looking at what I really wanted to do in the start, but it took years to actually get here, which is looking at how do you solve these problems, thinking of transportation in a bigger picture, not just profit maximization for car sharing, but transportation accessibility. Could you locate your cars, such as yes, to improve profit, which of course is the bottom line of Zipcar, but also to improve transportation accessibility, because what they're currently doing is they're putting all their cars in like downtown Boston, where there's relatively good public transportation. People have many options. Whereas, the suburban areas don't really have any alternative other than driving. And I think there, they're not connected to public transportation, but if you had car sharing, maybe that could be a way to solve like the first mile, last mile problem and overall improve transportation options in the metropolitan area. The other neat thing we're doing with them is now that they actually are collecting and archiving search data. So we actually have that, and we're using that to estimate demand, to understand better what the demand distribution looks like. And from a methodological perspective, what I'm excited about is, I think on the one hand, it shows that with very simple formulations like your preferred mixed integer program, you could really speed up the performance of general purpose discrete simulation-based optimization algorithms. And the reason why I find that particularly promising in the discrete space compared to the continuous space is, as a modeler, you don't have to necessarily spend a lot of time formulating that mixed integer program, because most likely there's something already in the literature that approximates well the problem that you're looking at. In the traffic space, that wasn't the case. There weren't really traffic models that would be that computationally tractable to be used as meta models. So it becomes a little bit, in the discrete space, a little bit more plug and play. Choose your favorite mixed integer formulation that exists and combine it with simulation data to improve the performance of general purpose discrete simulation-based optimization algorithms. We show that you can actually improve the scalability of general purpose algorithms. You can tackle higher dimensional problems. And the other aspect that I'm really excited about is, when I talk about simulation, often, especially in the transportation community, we think of really complicated traffic models that require a lot of data, a lot of work to just develop, validate, calibrate, and that we don't really have a good intuition on are these really accurate models. But if you think of actually having access to really high resolution mobility data, and you come up with sampling mechanisms like the demand estimation that we did to use that data disaggregately for optimization, that's basically simulation, right? The sampling process is stochastic. Now your simulator is not, a complicated, maybe discrete event or agent-based simulator, but it's a sampling process of which you don't really understand the supply-demand interactions because you haven't specified exactly what is driving demand. So I see it also as a way to make our optimization algorithms much more data-driven by sampling from that really neat high-resolution data that we have access to. And so what we're doing now, a lot more on the data-driven side with some nice data that we're getting for car sharing in particular, also demand estimation, demand calibration, looking at higher dimensional problems and the real-time aspect of it. One last thing that we did that, how I mentioned that most of our performance algorithms look like this. They just flatten out and don't do much. So one thing we've done is, what if you take your meta model and use it as a proxy for your sampling distribution? So instead of using it for such that at every iteration you minimize the meta model, which when you work with small computational budgets, your meta model from one iteration to the next doesn't change much. The fit of your parameters really don't change much. So you're solving very similar problems at every iteration, which is why you end up with, not much improvement. But what if you take your meta model or your mixed integer program and use that as a proxy of with what probability should I be sampling which points? That would be a good way to trade off better the exploration aspect, right? Because you wouldn't just be sampling points that have good performance, you would also be sampling points that, according to your meta model, don't perform that well, but maybe according to the simulator, perform differently or better. So we've done that in continuous space, and I think that's a good avenue to actually improve the performance of these algorithms across iterations, not just initially. Okay, so I hope with that to have illustrated some ideas of how I think we get the best of both worlds by exploiting problem structure. And so, of course, that means that you have to look at a specific subfamily of problems, in this case, some subfamily of transportation problems, not like general purpose algorithms, which are defined for a much broader family of problems. But I think it has very good potential to solve actual problems in transportation that are in need for of good solutions, and also a lot of potential to use a lot of the nice high-resolution mobility data that is now available. So with that, a lot of things I mentioned are, of course, product of my grad students, masters, and great PhD students, both of them, who are really the brains behind all of this. I'm just like the marketing person that comes and talks about it, and some really great faculty collaborators that have helped out throughout the years. And with that, I leave the space open for questions, comments.
Questions?
The first model, when you said A of x, how often do you, when you said when you go from time to time, you said you'll update the parameters but not the A of x, or do you update? Yeah. So how often do you change A of x? Don't you have to change? Would that A of x apply throughout the entire day of your operation?
So So this is the formulation when it doesn't depend on time. So it's a system of equations that is basically a stationary model of traffic. And so what we do is for every time interval, so let's say from 7 to 8, I have two time intervals, 7 to 7:30, 7:38. I assume that this system of equation holds, so that the specification does not vary over time. But what changes are these coefficients. I solve this problem for every time interval. So I have solved one for 7 to 7:30, one from 7:38. And I estimate these coefficients. For example, for 7 to 7:30, I estimate it such that this function minimizes the distance with the simulated coefficients, or simulated objective function from 7 to 7:30.
Correct.
So the coefficients beta k change across time intervals. Their estimates
so they
change.
hold good, so A holds good for the entire day, for example, like afternoon of 3 o'clock or
So
evening,
the specification does, but the parameters don't. But yeah, the description of how for a given demand that maps to a specific set of routes and hence to a given set of congestion patterns, that specification doesn't vary. And one thing that could be interesting is we use this polynomial here doesn't depend at all on time. So the correlation is really only captured in fitting the parameters, but it could be interesting to use a time-dependent general purpose function here that could more explicitly capture that correlation. So you could say, there's higher correlation with time intervals that are adjacent versus time intervals that are further away. And that, I think, especially for real time, I think that's the way to go, capturing explicitly more spatial temporal dependency through those general purpose.
Yeah, that was my point.
Yeah.
So I was getting to that.
So currently, none of this depends on time. Even the phi doesn't depend on time. But I think that's, especially for real time, that's definitely the way to go. And you could probably do that with really simple formulations. It doesn't have to become complicated. And it doesn't complicate your system of equations, your constraints. Yeah, good point.
Sorry, I have to leave.
Okay.
So the exploration versus exploitation, how do you convert your MAP solution to a distribution? Because you get a point estimate.
Okay,
for the
so
MAP solver,
basically,
right?
I'm going to add a blackboard. So basically assume, I don't have any curves. Assume, let's look at the MIP here. So the MIP, remember, number one, it's parametric. So it actually changes at every iteration. But for one of these, I actually have, so in the MIP actually, so in the discrete space, we haven't done the using this as a sampling proxy because you would end up with very similar solutions simply because it's linear. But in the traffic context, your meta model is actually typically non-convex. And so there you would say points that have good performance value, either high or low, depending on whether you're minimizing or maximizing, have high or low probability of sampling. So you don't have a uniform sampling distribution across your space. It is defined based on whether this lower fidelity model assumes or thinks that the point will have good performance.
So
with the MIP, we haven't generalized it actually using it as a proxy for the sampling distribution.
So as your iterative solver goes, you basically remember the solutions, and then you basically flip them into probabilities, right?
So initially, assume you haven't simulated anything, you use the A of x as a proxy for your sampling distribution. So points where A of x says they have good performance value, I want to give them
So
high
A of x
probability.
becomes unscaled probability density function.
Exactly.
Okay.
And then you can correct for it. As you collect simulation
yeah.
information, you can correct that sampling distribution based on what you've learned from the high resolution. Yeah. But initially, it's just A of x.
Okay.
Yeah.
From an application perspective, for your audience estimation model,
Yeah.
how do you validate your results?
So a couple of things. The traditional way to validate, so one really important aspect about calibration, so it's not a sexy topic. It's been around for decades in transportation, but I think it's a really important one, and I would say in the last 2 years, a bigger proportion of what I do is actually focused on different forms of calibration, because these tools, in one way or another, are being used by a lot of mobility stakeholders to make decisions, but the quality of the calibration is not very good. And we, as modelers, haven't done a good job at designing good calibration algorithms. So one way that they test whether the calibration results are good or not is these types of functions, graphs. So basically, on the y-axis, on the x-axis is your field count, so if you have speed measurements, flow measurements, and on the y-axis would be the estimated speed or measurements from your simulator. So if you look back at the objective function, it's plotting the YITs versus these expected values. And so you would expect a good fit would be something that falls basically along the diagonal, and a bad fit would not. There's a big challenge there, because even if, so you would say, oh, this is a great one compared to this one, but since the problem is underdetermined, there are many different solutions that could give you a really good fit, and we don't have yet calibration algorithms that are really telling us, are we fitting well the behavior or just these aggregate measurements? And so we've done some work, for example, at saying, if you had more detailed data, for example, one thing we did is with turning fractions, could you say anything more about actual fitting behavior? And the reason that that's important is because once I calibrate this, I'm now going to use my simulator to study a variety of maybe traffic management strategies, maybe congestion pricing. I'm going to use it to say which congestion pricing strategy should I deploy. But for that to be accurate, I need to be confident that the actual calibration of my, for example, route choice model is correct. So I have to make behavioral, I have to trust the behavior that I fit. Yet these, this type of validation doesn't say much about behavior. And so part of what we're doing is, if you had more high resolution data, could you specify a little bit more complicated calibration problems, but that would constrain much more the types of behavior that would be consistent with that type of more aggregate traffic data. So there's a lot of work there to be done in terms of, can we say anything about the behavior that we've calibrated? And often one of the big challenges is, once this is calibrated, the stakeholders would just take the model and assume it's perfect and then use it, right? And they forget about the fact that there's all these issues in calibrating and validating and even in the data. So I think there's a lot of work there to be done to develop better calibration techniques. Yeah.
So in your current model, you're validating against the aggregated traffic counts honesty.
Uh-huh.
And what is the average mean square errors?
So for the dynamic case, we end up with, for Singapore, which we did from 7 a.m. to 9 a.m. in 30-minute time intervals, the root mean square error across a variety of experiments is in the order between 15%, if it's normalized root mean square error percentage, to about 20%. And then the standard metrics, standard general purpose algorithms, if you terminate them early on, they're more in the order, I believe, of 60 to 70%, simply because they're very sensitive to your initial condition. Yeah. But I wouldn't say that because you've replicated really well your measurements, that it's necessarily a good calibration. I think there's a lot of things there.
Well, I think since the time is running out, I want to officially wrap up the seminar. If any more questions, we can talk offline. And then after that, we'll go to the lunch. Faculty are all welcome to join our lunch at ITIS. Well, let's thank the speaker again. Thank you. Thank you.
Some time, I can check the time.
Can you join our lunch? That's the only time we have.
Oh, there's only time?
Yeah. Ali is going to meet with her after the lunch, and then she's going to be on.
Okay.